Good to see you. Sorry, I haven't been able to be present at much of this workshop. There's something simultaneously going on in Boston, another workshop that I've been tied up with. So anyways, definitely please interrupt me with questions throughout this talk. I would rather not get through all of the slides than just give a virtual talk and not get questions. So that's my main hope, and I plan to go slow. The main result that I want to tell you about is based on this paper with my former student, Jiahua Tian, who's now a professor in Shanghai, and Joydeep Naskar, a student of my colleague Ning Bao. And the basic statement is that we have a new way to define conformal fields, such that all of the symmetries are what we would expect, and we can compute correlators and do conformal block decompositions and so forth. So I'd like to tell you a little bit about that. If you're interested more broadly in the perspectives I'm talking about today, I might recommend this machine learning TASI lectures that I gave a few months ago and that came out in August. Okay, so before I get to the main event, let me tell you a little bit about our NSF AI Institute for Artificial Intelligence and Fundamental Interactions. This is the AI and Physics Institute in the Boston area, MIT, Harvard, Northeastern, and Tufts. And we are interested in advancing physics knowledge in a physics for ML direction and also an ML for physics direction. Definitely, if you're in the area, you should come by, but you can also connect with us online via our website. Before I get too much into ML for physics, which is what I'll be doing, I want to give a little bit of a flavor of why physics for ML might be a useful way to think about things. So I'll begin with a little bit of a discussion of a couple of axes of choices you can make in ML to try to maximize learning. The essential goal in a machine learning problem is to, given the learning problem and the data, you'd like to maximize the learning, the generalization, the ability of the neural network to make good predictions on unseen data and so forth. And two of the axes, which are not the ones that I'll talk about today, are the choices of an architecture. So for example, do you take a vanilla neural network like a multi-layer perceptron or a convolutional neural network or a Kolmogorov-Arnold network or famously a transformer? That's sort of this axis. And then there's another question, which is what optimization algorithm do you use to train your neural network in the first place? So the neural network could be trained by multiple different algorithms, for example, gradient descent or stochastic gradient descent, et cetera. And so this is some sort of other axis. And if you pick a point on these axes so that you are fixed architecture and fixed optimization algorithm, the claim is that once you fix this, that field theory is a useful way to think about learning. I'd like to tell you a little bit about that. So field theoretic thinking in a machine learning direction goes this way. The first thing that you should keep in mind is that in machine learning, there are trajectories associated to a fixed architecture, data, and an optimization algorithm. So namely, first of all, my neural network has some parameters, theta, that live in some big real space. I'm taking them to be real parameters. And those thetas, those parameters, can evolve in time. But those parameters themselves appear in a function that I'll call phi sub theta that live in maps from RD to R. I'll just take scalars for the moment just to keep things simple. They live in R. But because the maps depend on the parameters and the parameters evolve in time, there's also a trajectory through the space of maps, through the function space associated with this neural network training. And finally, if you evaluate that function on some particular input X, there's also an evolution in output space. So machine learning is about trajectories through parameter space and associated function spaces and output spaces. And that's just a way of saying that your predictions are evolving in time and they are determined by a function that is evolving in time, in training time. Now, there's also another fact that these parameters, the initial conditions for these trajectories, are based on how you draw your parameters at initialization. This means that theta is drawn from P of theta. And if you restart your computer many times, you get many different initial conditions for your trajectories through function space. And what that means is sort of that there's nothing fundamental about any initial draw that you do. And so in particular, you might try to ask questions about the statistics in this ensemble of functions, that each draw determines some parameters, and those parameters determine an ensemble of functions. And you can compute expectation values in that ensemble. And when you put words on this, X is the input, phi of X is a neural network prediction. You're taking an ensemble average across all different initial values of theta. That's the mean prediction. This is the expected prediction in this ensemble of neural networks. And the point is that we know that object very well in field theory. An expectation value in an ensemble of functions of the function itself, of the function's output, is what we call the one-point function. And similarly, you could compute the expectation value of a product of neural network outputs, which you might use to compute the variance. And that's what we call the two-point function. So already, doing very little work, our neural networks have given us not just one function, but in fact, an ensemble of functions weighted according to this p of theta. And we have a field theoretic way of thinking of this. The average neural network prediction is the one-point function, and the two-point function is the product. So ideally, you want to put these ideas of the dynamics and the statistics together and understand average and covariance of neural network predictions as the ensembles evolve, and also how hyperparameter choices affect them and the ability to scale up. That's sort of some of the things that have been happening in machine learning the last few years with respect to some of these things called NTK and MUP and DMFT and so forth. But the essential idea is that this way of thinking about machine learning, I think, is a useful one, because if you wanted to be able to theoretically understand something, trying to understand how the average neural network prediction evolves in time seems very important from a theory of ML perspective, but that's just some one-point function that is evolving in time as the parameters are updated. Okay, so I think this is a useful way to think, and this is the perspective that I take throughout my TASI lectures. This is all in the for machine learning direction, which is not what this talk is about, but I wanted to mention it in case you're interested in these directions. And here are the TASI lectures that I mentioned, and I definitely take this perspective. We're a bunch of high-energy theorists here, so in particular, and maybe some mathematicians as well. So this exposition on neural network theory emphasizes a field theoretic perspective that'll be familiar to many of you. So for the rest of the talk, I want to talk about symmetries, and specifically conformal symmetry, associated to a fixed neural network ensemble at a fixed time slice of training, especially initialization. Really, everything I've said so far is for machine learning. Now I want to do it for physics. And I want to use these neural network ideas as a new way to define a field theory in the first place. And we'll talk about how to do that. But then once I have a new way to define a field theory, you can ask, if I have a new way to define a field theory, can I get many of the things that I know and love from field theory? And we'll try to get CFTs in particular. Okay, so these are my wonderful collaborators. Just appeared as a little too strong. This was a month ago, something like that. And I've had many collaborators on related projects. This is Joy Ning's student and Tian, who's a professor in Shanghai. So there's really only 3 points that I want to get in the first section, which is like the setup for the whole thing. Why neural networks and field theory, what is CFT, and sort of why do we care, and also the embedding formalism. This is going to be a little bit elementary for a high energy theory audience, so I'll try to focus on some of the technicalities towards the end, but it's important to set the stage. And then after that, sorry, and crucially, not after that yet, the embedding formalism is this idea of Dirac, that the Lorentz group is in some sense equal to the conformal group in a way that if you can handle Lorentzi types of theories, you might be able to handle CFTs. And I'll talk about how to do that. And this is the essential idea that we use in a neural network context. The essentials of our formalism is a new construction of conformal fields. I don't yet know how far this can go, in the sense that I don't know if all CFTs can be represented this way, etc. But at the very least, it seems like a new way to define a CFT such that conformality is ensured. And furthermore, it allows you to do computations in a new way. So for example, in certain cases, we'll have exact 4-point functions. And then we'll use it. We'll take some we'll see some examples. We'll have some free limits. We'll do deep nets and recursion, and we'll do the free boson and some mixing. Okay. Any questions sort of so far? Okay. I'll continue. The setup, the following three key points. The first is neural networks and field theory. The second is about CFT, the big picture, the what and the why. And the third is about Dirac's embedding formalism. This is where some of the technicalities really enter. So first, before we get into conformal field theories, let's just talk about field theories. So why do neural networks and field theory have anything to do with each other? As I already emphasized, a network is a function that depends on some parameters that's in the space of maps, in this case from RD to R. You can take more general domains and codomains for your functions if you want, but I'm going to focus on scalar field theory for now, truly in the tradition of Coleman, and I'm just going to have all of my maps be maps into R. These parameters are drawn at initialization. So this is really a family of functions that depend on theta. So for any fixed values of these parameters theta, I have a single map. But really, I have a family of functions that are weighted statistically according to the probability of those parameters. And what that means is that given the statistics associated to these maps, I can compute some sort of expectation value in this ensemble of maps by integrating the function itself or the product of the functions against the density on neural network parameters. And then if you wanted to, you could add dynamics for learning if this were a different talk. So there's already 1-point functions and 2-point functions. And similarly, you could take the expectation value of phi of x, phi of y, phi of z, phi of w, and get 4-point functions. So this correspondence, the idea is that the essential neural network information of the architecture here and the density on parameters that the parameters are drawn from defines a field theory in the sense that I can have correlators over here. I have fields and I have correlators, and that's sort of the essential data of a field theory. So this defines a field theory, and the partition function is given by this object, the integral against the density on parameters of e to the integral j phi. Okay, so this is what we normally have in field theory. And of course, in the usual way, we turn this partition function into these correlators by hitting it with appropriate j derivatives and then setting j to 0. So it's completely the standard thing. But this is not the form of the partition function that we normally talk about in Euclidean field theory in our classes, in our normal research, etc. There, our partition function looks like this. It's Feynman's path integral. I still have this e to the j phi behavior. That e to the j phi is just there to let me take j derivatives and pull down phi's and get correlators. But now, instead of this density on parameters, I have a functional density where e to the minus s determines the density on functions. And so this is the canonical way to define a field theory. And this is a different, but apparently new way to define a field theory that was first motivated by what Radford Neal was doing in his PhD thesis in the 1990s. And basically, with this different way to think about field theory, we can ask, what can we do? And in certain cases, we can get non-perturbative exact calculations, because it could be that for certain theories, this integral, for instance, with 4 phi's stuck in instead of 2, would give you a 4-point function that you can compute analytically. So this is sort of the key slide. Are there questions on the setup, why this is a field theory, or what's different, etc.? I'll keep asking throughout in case there are questions. So given this notion of a field theory, where I have a very minimal notion, I say that anything I mean by a field theory has to have fields, and it has to have correlation functions. Things that don't have correlation functions or fields, I wouldn't necessarily call a field theory. So given that minimal definition, you can ask, can I engineer my defining data, this neural network architecture and parameter density, to get a field theory plus something else, x, where x could be that you want a quantum field theory, or you want a Lagrangian field theory, local Lagrangians, or you want some other notion of locality, or maybe you want some symmetries. And this is sort of extra widgets that we add for theories that we care about to supplement our correlation functions and fields themselves. And then this is an engineering question. And so for today, x is equal to conformal symmetry. So what is a CFT? It doesn't need explanation in this community, but a field theory with conformal group as the symmetry is a CFT. Those are invariant under coordinate transformations that leave the metric invariant up to an overall x-dependent scale factor. The Euclidean CFT group in d dimensions is SOD plus 1, 1, and it's made up of rotations, translations, scalings, and special conformal transformations. Phase transitions are described by conformal field theory with universality. I had GPT-4. I asked for a picture of Boston with the Charles River boiling. And you can see that the water looks like it's bubbling and the Charles River is beginning to boil. This is obviously the Prudential Center, which is a famous building in Boston. And it's actually near the triple point, because you can see over here that there's actually snow in this picture. So there's water vapor and boiling water and snow all in the same picture that GPT gave. This is some sort of phase transition happening in the Charles River, But of course, the liquid to gas phase transition is one of the classic examples of a CFT, for instance, that you can find in Heskin and Schroeder. On the other hand, another reason why we care about CFTs, not just from the point of view of phase transitions, is that we think of it as an organizing principle for field theory, in the sense that if we imagine some abstract space of CFTs and you have some CFT in the UV, that if you do some perturbation of it, some relevant deformation, that is going to trigger an RG flow that leads you in principle down to some other CFT in the IR. And so CFTs are sort of the bookends of RG flows and therefore give an organizing principle for field theory. Okay. So where does Dirac come in? I encourage you to look at this group. Think about it for a moment. What Dirac says is that the conformal group is SOD plus 1, 1. That is precisely the Lorentz group in D plus 2 dimensions. And Lorentz is equal to conformal from his perspective there. Now the dimension changes, so you don't just get it for free, but the idea is somehow that Lorentz group in D plus 2 dimensions is the conformal group in D dimensions. And so you might ask, can I come up with a way to do Lorentz invariant field theory 2 dimensions higher and then push it down to a Euclidean CFT? So to give you a little more meat on this embedding formalism, it goes like this. The key fact is that the Lorentz transformations in D plus 2 dimensions are inducing nonlinearly realized conformal transformations on the D-dimensional projective null cone. And so in particular, every Lorentz generator in D plus 2 dimensions has to become a conformal generator 2 dimensions lower. Here I have I runs from 1 to D, the Euclidean index. So this is just, Lij is therefore just SOD rotations in the CFT. Then I'm in light cone coordinates. So L plus minus on the Lorentzian space can be shown, that's one generator, right? That can be shown to be the scale transformation. Translations in the CFT and special conformal transformations both come with a vector index. They're determined by a vector. So I better have D of them. And indeed, those are from Li plus and Li minus, respectively. And so the idea that's in many CFT lectures, for example, this is from Rikov's EPFL lectures, is to think of these Lorentz transformations 2 dimensions higher as giving conformal transformations on the projective null cone. So the first thing that we do is we take our Lorentzian coordinate, and we have a D-dimensional Euclidean coordinate here. We have x0 and xd plus 1. And then we're going to combine this into light cone coordinates in the standard way, combine these two. We go to the null cone here, and then we also projectivize and do something called choosing the Poincaré section. And choosing the Poincaré section, we get this 1 here. The light cone, the null cone condition gives me x squared here, and x is a completely free coordinate. So by starting in D plus 2 Lorentzian and restricting to the Poincaré section of the projective null cone, I get a copy of RD. Okay, this is the key insight. So the idea is somehow that if you can do Lorentz invariant stuff up here, you can push it down to conformally invariant stuff on the projective null cone. Let's talk about this from the perspective of modern CFT. This embedding formalism is textbook in modern CFT. And the conformal fields, if you think about, normally people are not going the direction I'm going, which is to define CFTs in terms of Lorentzian theories. Normally, they're thinking of some CFT that they already know something about and lifting it to the embedding space. And in that lifting, the conformal fields get lifted to a field on D plus 2-dimensional Minkowski space that is homogeneous. And it restricts back to the conformal field when you restrict it to the Poincaré section. And the primary reason that people do this is that Lorentz symmetry sheds some simpler new light on the conformal objects, for example, the correlation functions. It gives a nice organizing way to think about CFT transformations. So in this language, the 2-point function, for instance, of the fields on the embedding space is of this form, 1 over x1 dot x2 to the delta phi. This is this homogeneity condition here that is ensuring this scaling. Notice that this dot here is the D plus 2-dimensional Minkowski metric. And so this is a completely Lorentz invariant 2-point function, and indeed it's homogeneous. When you take this 2-point function and you restrict it to the projective null cone up to a constant that I may have dropped, this x1 dot x2 becomes x1 minus x2, where these are now the d-dimensional coordinates of the CFT. And this is exactly the structure that a two-point function has to have in conformal field theory. Similarly, the four-point function has to satisfy, can be taken in the Lorentzian space and then pushed down to the conformal coordinates. And it takes this form, where x12 is x1 minus x2. And so this is x1 minus x2 raised to the 2 delta. And there's some piece left over here that is canonically known as GUV, where U and V are conformal cross ratios. And for the theory to be conformally invariant, these conformal cross ratios have to these GUVs have to satisfy conformal symmetry. Have to satisfy crossing symmetry, which is this condition here. So this is the modern CFT approach to thinking about the embedding formalism. And in particular, if you had a conformally invariant theory and you knew these G's exactly, they would automatically satisfy crossing. But if you're doing something where you're trying to search for CFTs in a bootstrap sort of way, crossing is a condition that you have to impose that is necessary for conformal symmetry. Okay. So the embedding formalism is a powerful tool for understanding how conformal invariance constrains correlators of known CFTs, or CFTs we're searching for with constrained optimization. But the question that I want to ask in this talk, which is really our main result, is can we use the embedding formalism to construct CFTs? And the answer to that is yes. So here's the essentials of our formalism. Are there any questions on the embedding formalism before I turn to the new stuff? Maybe everyone knows this. I'll continue. Okay. So we're going to ask, can we use the embedding formalism to construct CFTs? And to do this, the way that I want to do it is I want to start with an SOD plus 1, 1 symmetric homogeneous theory on RD plus 1, 1. Homogeneity was important in the whole construction. The SOD plus 1, 1 here is saying that I have a Lorentz invariant theory. And then I'm going to take that Lorentz invariant theory, and if I can define a theory here and do computations and then restrict to the projective null cone, I get a CFT. That's the essential idea. So the constraints on the D plus 2-dimensional theory are the following. First of all, this homogeneity. Second of all, one needs Lorentz invariance. This is the crucial symmetry. And third of all, we need to have correlators because we don't have field theory without correlators. So I'm going to go through each one of these constraints one by one and sort of tell you where the neural network construction is actually kind of important. And that also explains why people haven't done this before, because I think that this is such an easy idea once you see it. It sort of begs the question, why, if this is a new way to do CFT, why haven't people done it? And the homogeneity is the key thing that has been missing previously. So here's the principle. I'm just going to be defining a neural network field theory in D plus 2 dimensions that is Lorentz invariant. And the 2 bits of data for any neural network field theory is P of theta, which is the thing you integrate your fields against to get correlators. And there's also the information of the network architecture, which is a choice of a particular functional form. So because I need homogeneity, this just constrains the neural network to be a homogeneous function of appropriate degree that determines the conformal dimension. And I'm just going to choose that neural network to be a homogeneous architecture. For instance, if you take a standard deep neural network of this form and you make all of the activation functions homogeneous, for example, homogeneous powers of some sort, then you get a homogeneous neural network. Alternatively, you can imagine that you have compositions of homogeneous polynomials. This could hurt expressivity, but it can potentially increase control and connect you into other beautiful mathematics. But homogeneity is something that we can choose for our neural network architectures, and we're going to choose it because that's essential to the construction. Principle 2 is Lorentz invariance. So we can show it at the level of partition function, but here we'd like to think in terms of correlators. So if we recall what's happening in terms of the correlators, we have our correlators expressed not by integrating against e to the minus s of the standard Feynman path integral, but rather these parameters, I call them capital theta now, because these are the parameters of the Lorentzian theory, and the capital x's are the coordinates of the Lorentzian theory. And I compute my correlators by integrating against this parameter function P of theta that in a standard setting would be a density. And we need these to be Lorentz invariant. So the mechanism that we came up with a few years ago for demonstrating symmetry in this case is, first of all, to choose a P that is invariant with respect to your symmetry, to transform the fields under the symmetry, and I'll give you an example in a second, to absorb that transformation into a parameter redefinition. And then, because P itself is invariant, you can do a redefinition of the parameters that leaves the whole thing invariant. So in our case, we'll choose P to be Lorentz invariant. So once again, I'm imagining a case where I have some parameters appearing in the neural network phi. I'm going to act on these correlators on all of these x's with a Lorentz transformation. So I have an L in there and an L in there. In many architectures, this is the construction we're using, you can absorb that L into a redefinition of parameters that are interacting with the x's. That redefinition, if it leaves this density invariant, leaves the entire correlator invariant, and you have Lorentz invariance. So that's
So what would be an example of such a P?
I'll give you an example in just a moment. But if I not in the Lorentz case, let me do the simplest case, which is rotational invariance, which is a simpler version of Lorentz invariance, if you'd like, after Wick rotating. A very famous rotationally invariant density is the multivariate Gaussian. E to the minus 1 over 2 sigma squared sum on xi squared is constructed up in the exponential out of, sorry, I should call it theta, is constructed out of theta dot theta. And theta dot theta is rotationally invariant. So the multivariate Gaussian, sort of one of the most simple densities of all, is a rotationally invariant density. You can, if you'd like, you can Wick rotate that and get something Lorentz invariant. And we'll talk about that in a second. So that's actually not the hard part. The hard part is to come. And then the principle 3 is that we need the correlation functions to not diverge everywhere. We need them to be well-behaved enough so that we actually have a theory. And this is this question that was sort of just raised about what's a good Lorentz invariant P. And you have to be careful about how to do this. And I'll give you learning the pain of this by example. This is the hard principle. So the natural idea is just to take any rotationally invariant P and to Wick rotate it and get something Lorentz invariant, right? That's how we often get Lorentz invariant things in field theory. So let's take our famous example. Here is the multivariate Gaussian that I just mentioned, where I've split some of the parameters, called them theta 0, and the others are all organized in this thing that I'm calling theta vector, okay? And I've split it this way because, of course, I want to separate. These are all created equal, and I have full SOD plus 2 invariance in here. But I want to signal off 1 as the Euclidean time so that I can Wick rotate it and go to Lorentzian. And so when I Wick rotate it, this in this equation flips the sign, which a priori you say, great, flip the sign. I've got a Lorentz invariant P of theta. Life is nice. But then when you think about this is something that when you integrate over all thetas, this thing does not want to converge anymore. Famously, the integral of the Gaussian is finite, but the integral of the wrong signed Gaussian is not. And in particular, these variables are all independent, so you can do just the theta 0 integral, and that thing diverges. So that's the problem. And in particular, that divergence we'll call divergences everywhere in all of the correlators. So this is a theory that is homogeneous and Lorentz invariant, but formally speaking, all of the correlators diverge because the wrong sign Gaussian. The correlators have an essential singularity. So that's why you have to be careful. The first two principles are easy, homogeneity and Lorentz invariance. Getting something finite is hard. So this homogeneous and the formal Lorentz invariants are easy by this choice of architecture and P. Formally, the thing that I write down here, even in this case, is Lorentz invariant, but it's actually infinity everywhere when you try to do these integrals. Maybe there's some subtlety, but this is not what we want. Okay. So just to recap the formalism, I'm going to state the principles, and then the point is you have to have them all be satisfied. We have a Lorentz invariant theory on Rd plus 1, 1 that we restrict down to a CFT on Rd. And we get this theory by specifying a homogeneous neural network, which gives me a homogeneous ensemble of functions. I have Lorentz invariance from coming from a Lorentz invariant P of theta. And I have correlators from doing these computations in parameter space. And we have to do some work to make sure that they're well behaved. So this is a cake. And this is a decorated cake. And the point here, 30 minutes in, is that you've already seen all of the important ideas that you need to remember, should you want to remember the details of this talk. And the rest of the talk is basically just decorating the cake. Things that are not generic to the formalism, that are corollaries, that are important, but the essential formalism so far is all there. So I'll give you a simple pedagogical example. I'll give you a clever example. I'll take a generalized free theory limit. I'll construct deep neural networks and talk about recursive conformal fields. And then I'll talk about the free boson and mixing. But maybe since all of the essence is already here, I'll pause for a moment in case there are questions with the construction rather than the corollaries.
Yeah, I still have a question here. So given that you have to do something to ensure that you have well-defined correlators, that will not take you out of the realm of conformal invariance, that regularization procedure. It will not, right?
Oh, I'm sorry. Sorry. Yeah, you need to make sure that your correlators aren't diverging everywhere. So it's some sort of regularization procedure, or you just don't have the singularities to begin with. And you need to make sure that whatever you're doing, Lorentz invariance needs to be preserved.
Okay.
You could imagine some case that's interesting where the regulator weakly breaks Lorentz invariance, and then you would have some weak breaking of the conformal field theory, of the conformal symmetry. But everything I'm going to do here is going to be well, okay, we can talk about that, but in the simplest case, it's going to maintain Lorentz invariance exactly.
I have a simple question. Just
yes, hey, Nana. Sure.
Hi, hello, Jim. Hi. Yeah, so it's quite interesting, but I have a question. So your neural network is a mimicking of the CFT. So the neural network has all the information of the CFT encoded, included the correlators?
It has, sorry, is that the question?
Yes.
Yeah, the key thing in any of these settings, so let's not worry about conformal symmetry for now, is that it's not just the architecture of the neural network. It is also, coming back, did I go too far? Yeah, this is what I want. It's also the density on parameters, because I know you've worked with neural networks. If you restart your computer and you didn't set the seed, you get a different neural network, right? Because the parameters are different at initialization. Because the parameters are drawn from some some density on parameters. And so the point is that the neural network together with P of theta really defines an ensemble of functions. And you can compute expectation values in that ensemble of functions by integrating against P of theta. So it is not the architecture alone that determines the correlators. It's the architecture, which is the functional form. So you could just take this to be a standard deep network, for instance. Take it really to be anything. This is the architecture. It's the functional form of phi of theta. And you integrate it against the density on parameters to get the correlators. So it's really both. The essential defining data is this. And from this information, which anytime you start a neural network on your computer, you're always specifying a functional form. And your code is always implicitly doing a draw from some parameter density. This defines a partition function, and then that lets you get the correlators. So the essential definition, the essential answer to your question doesn't have anything to do with conformal symmetry because it's bigger, but then I'm doing these extra to get conformal symmetry.
Okay, thank you. Nice.
Yeah, sure. Thanks for the question. Okay. Got to go back to the cake. Were there any other questions at this point? Let's keep going through. Probably won't necessarily feel the need to go through all of these in detail, but I want to show you one example that's very clearly working, and then maybe I can take some questions. So let me tell you how we can use this construction. So I'm going to give you a solvable non-unitary example. I'm not going to worry for a moment about unitarity. I'm just going to worry about conformal symmetry. And the point of this example is not to be interesting, it's to be pedagogical and to demonstrate that this works. So the approach that we're going to take here, my whole construction on the last couple pages was this half of this diagram. But one way that you can get here to this theory is by starting with an SOD+2 symmetric homogeneous theory on RD+2 and Wick rotating. And when I do that, I end up with a Lorentz invariant theory, and I can restrict down. So what I'm going to do is I'm going to solve the Euclidean D+2 dimensional theory, Wick rotate to get this theory, and then push down to get the CFT. So here's a silly theory. Here's my neural network architecture. I'm calling this the Euclidean neural network architecture. And indeed, because I'm doing rotation symmetry in D+2 here, Wick rotating and coming down, I'm going to choose my density on thetas to be rotationally invariant. And then I'm going to take my architecture to be the silliest architecture in the world, which is just taking my parameters and dotting them with x, where x is a Euclidean d+2 vector. So this is a family of maps from Rd+2 to R, where the family is parametrized by these thetas, and those thetas are given statistics based on the fact that I have a density on parameters. So this yields a Lorentzian theory when you think about computing the expectation of phi of x, phi of y, integrating against any rotationally invariant density. It turns out that that tensor in this detail is, there's a Kronecker delta, and that Kronecker delta takes a dot product, and you end up with x1 times x2. I've chosen a particular normalization of the moment, of the second moment here. But I end up with x1 dot x2, where this is the Euclidean d+2 metric now, and this is fully rotationally invariant. Similarly, I can compute the exact 4-point function in this setup, where mu4 is the fourth moment of p of theta. And the tensor structure associated with rotationally invariant theories here gives me x1.2, x3.x4 plus permutations. These are the exact correlators in this theory for any rotationally invariant p of theta. I did normalize such that I took the first moment to give me exactly this, but mu4 is the fourth moment. So when you have this structure, this is a rotationally invariant. I'm sorry, I'm getting a little turned around. This is the rotationally invariant theory. In Euclidean, this would be the Euclidean metric, and then I Wick rotate to get the Lorentzian theory, where this is the Minkowski metric. Then it's fully Lorentz invariant, and I push down and I get a CFT of this form, where the U's and V's are the conformal cross ratios. The details of this parameter density enter in two places with this mu4 here, and it also enters the rotational invariance, enters the tensor structure that gives me Lorentz structure here and pushes down to conformal structure here. So this is an interacting CFT with an exactly computable 4-point function. This is specified. GUV is normally left unknown. People love parametrizing things this way, but in this case, we have actually exactly computed GUV. It's right here, and it satisfies crossing. So this is a conformally invariant theory by construction. Okay, so that's a very simple example. Not the most interesting example, but it proves that this works. The homogeneity was easy. This is a homogeneous neural network because if I scale x, I scale phi, and the scaling dimension is 1 in this case, which means that the associated conformal dimension is -1. The symmetry comes for free, and then I actually compute the correlators, and I see that they're finite. On the other hand, I can try to do a unitary example using amplitudes techniques. So this satisfies a necessary condition from unitarity coming from the unitarity bound. So here in this case, I'm going to, instead of, in the previous example, I had theta.x. Now I have 1 over theta.x as my architecture. I'm going to start directly in the Lorentzian theory. I'm going to take p of theta here to be 1 over theta squared plus 1. This is technically not a probability because in Lorentzian, I can end up with this correlator with this becoming negative, but I can still write Lorentz invariant correlators, and I can still try to evaluate it in this way. And so this would be the 0-point function if you'd like, because I don't have any insertions of phi. I'm just integrating the parameter density. And you might ask yourself, does anyone know how to evaluate this? Well, this actually right here looks like a one-loop Higgs integral for the mass correction, this 1 over p squared plus m squared, restricted to the case that m squared is 1 and that p squared is theta squared. Yeah. So this is some Lorentz invariant thing. And in field theory, the way that you compute this and regulate is via dimensional regularization. But put differently, homogeneity and formal Lorentz invariance are automatic here. The only open question is finiteness of the correlators. And generally, that's true in these formalisms. And so then the question is, these integrals that we're trying to compute that represent the correlators, we need them to be finite. They're Lorentz invariant. And you ask, is there any community in physics that is really interested in computing Lorentz invariant integrals and making sure that they're finite? And that's exactly what the amplitudes community is doing. And in particular, given that they have lots of techniques and tricks for computing and understanding Lorentz invariant integrals and their finiteness properties, we use some of those techniques. So we have something called integration by parts identities, which give rise to differential equations that you can solve. And in this case, we are able to compute the 4-point function here. It satisfies crossing. You can do a conformal block decomposition. You can infer certain properties of the OPE, et cetera. So this was a case where we used the techniques from the amplitudes community to actually be able to evaluate Lorentz invariant integrals in dimensional regularization. So that's the idea. Yeah.
So you pick the distribution to
Damian, hello.
Hey, Jim.
Yeah.
You pick the distribution to be SOD+2 invariant, right? Or the density, the P of theta.
In this case, I did, and then I Wick rotated. In this case, I'm working directly with the Lorentz invariant density. This theta squared means theta Minkowski theta. But yes, that's a technicality.
So, and then phi of x is also invariant, right?
Phi of x is not invariant, actually. That's not how the mechanism works.
I see.
So the thetas don't rotate. So you might imagine that your neural network picks parameters that are 1, 2, 3, 4, 5 once in a while. So they don't rotate. And what that means is that when you do a Lorentz transformation on phi of x here, so phi of Lx is theta dot Lx to the -1. But if you see that here, Damian, I've transformed the field. And indeed, in field theory, symmetries are not symmetries. You don't leave the field invariant, you leave the partition function invariant. So the field transforms in a way that there's a little L right here, or a capital lambda if you want that for your Lorentz transformation, whatever you call it. And then I could say, okay, but I'm going to do that. I'm going to redefine a new parameter. I'm going to call theta prime to be theta times L. And so that transformation gets absorbed into a redefinition of the parameters. But then when that redefinition appears here, if this thing is invariant under that Lorentz transformation, which it is, then the whole thing's invariant. So that's the trick. We transform the fields. They transform non-trivially. We absorb the transformation into a redefinition of the parameters. And if your parameter density is invariant, then you end up with invariant correlators. That's how it works.
And in principle, this can be generalized to different representations.
Exactly. It can be generalized to different representations, many different cases, et cetera. I think the mechanism is fairly general. It took us a little while to recognize that it was quite what we want 3 or 4 years ago when we did this. But the essential point is that a global symmetry in field theory is not something that leaves the field invariant. It leaves the ensemble of fields invariant as measured by the partition function.
Okay, thank you.
Yeah, sure. Great question. Good. Okay, so just to mention a few other results and then I'll conclude. So we can also get deep networks and recursive conformal fields. So there's an idea, this is pretty detail oriented here, so maybe I'll just sort of state the idea. There's an idea of a CFT layer where the first layer of the neural network is already sufficient to ensure your conformal symmetry. And so I have a first layer that takes in my x's, it ensures conformal symmetry. I'm always assuming I have finite correlators. And then if you just take homogeneous layers after that, every layer down the deep neural network is actually defining a conformal field. So there's some notion of recursiveness of the conformal field as you go down the layer and you get different conformal fields at each layer. And in particular, you can sometimes relate the CFT data. If your jth layer has homogeneity delta F, and the previous conformal field has homogeneity here, scaling dimension, then the new scaling dimension is just the product of the two. And similarly, you can relate the 4-point functions to each other. And for deep linear networks, there's actually a detailed relationship between the conformal 4-point function at layer L-1 and the conformal 4-point function at layer L. So this is nice because I can get the story working in the first layer, and the symmetry properties of the first layer, as long as I preserve homogeneity and finite correlators, are enough to guarantee that at every layer I'm conformal, which is really cool because it defines some sort of notion of a recursive conformal field. There's also a free theory limit. So this is a story that I've worked on in many cases, and we want to do it in the CFT case. So the idea of the free theory limit is that I'm going to have a conformal field here, phi I, that are independently and identically distributed. Any architecture in our construction works here. And what I'm going to do is I'm going to multiply them by some parameter wi, which are all drawn IID. I'm going to sum them up and take a 1 over root n. And this is basically saying I'm taking a normalized sum of some independent and identically distributed functions here that have conformal invariance in their correlators. And I take the large n limit, and that's where the central limit theorem comes into the game. So the central limit theorem basically tells you that, that this theory as n goes to infinity is going to be Gaussian distributed. But at all n, in fact, I can compute the CFT data associated to this field. And what you get is this. This is the 4-point function. The 2-point function is the same for all n. But the 4-point function is the 4-point function of this theory, the phi theory here, and it's suppressed by 1 over n. And then I have this 1 minus 1 over n here, which is the is this GUV that determines the 4-point function of the free theory. And so the point is, as you crank n to infinity, this piece here shuts off, and you're mixing in the 4-point function of the free theory, which of course is not interacting and is a completely disconnected 4-point function. So this n is interpolating between the conformal fields I constructed here and some sort of free theory limit in a way that's mixing them. So I can get the free fields. You can also ask, can I just get the free boson, the standard free theory that people study? So this has dimension d minus 2 over 2. You can do that. This is this d minus 2 over 2. It's the same thing I did, but I just fixed the dimension to be d minus 2 over 2. So that's how I get the free boson. And so just to conclude, which gives me a few minutes for questions, there was the part that was like the essence of the cake, and then I put the icing on. I really care a lot more that people understand the essentials of the construction rather than the corollaries. But the essentials of the construction are that I have some way to define a theory here that is Lorentz invariant that pushes down to a CFT. And that theory had principles that needed to be satisfied. Homogeneity, and I get that from a homogeneous neural network. Lorentz invariance from a Lorentz invariant P of theta. And then I need to make sure that the correlators are finite. And I can compute these correlators in the way that machine learning people do. The key thing, I think, that, this idea is pretty simple, and I'm claiming that it gives you a new way to define a CFT. The key thing I think that people were not considering before that is essential in neural network field theory is that you specify the functional form. The functional form is the architecture. We don't normally in field theory say, I demand that all of my fields are homogeneous. That's not what we do. And we don't specify a functional form. Rather, we specify a functional density. And then any field, you may evaluate its probability in that functional density by e to the minus s, but you don't constrain the form. That's not how you do it. So because in neural network field theory, we get to specify the form, we just get to specify this homogeneity for free, and then we're basically done. There's this decorating the cake. We had a simple pedagogical example, a clever example, a generalized free theory limit, deep nets and recursive CFTs, and then the free boson and mixing. But really, I'd like for you to remember this and the fact that homogeneity came from the neural network construction. So I have a new way to define a CFT. Dirac tells us Lorentz equals conformal. That is the whole thing motivating it. We start in the Lorentzian picture and move down to the conformal picture. One thing that might have been implicit that I didn't explicitly say is something that's unusual about these theories is that these Lorentz invariant theories in d plus 2 dimensions do not have to be translationally invariant. And that's an unusual thing because normally, any time in normal field theory we consider Lorentz invariance, we demand full Poincare. And the reason that that's true here is because what I really care about is a CFT in d dimensions. And the translations in the CFT comes from the Lorentz transformations 2 dimensions higher. So you do not have to demand translation invariance in the higher dimensional theory. You can get away with just having Lorentz invariance, but breaking translation invariance, while still giving translation invariance in the CFT. So that's the idea. Sorry to end on a technicality, but thanks a lot. I'll take a couple questions and we can go from there.
Thanks a lot, Jim.